All right, welcome back to the first main video in 3.2. First, we're going to kind of just review Theorem 2.16. This example is really going to be the same idea as the exercise warm-up 2. So if you want to do this one on your own, pause the video and then fast forward after you're done to check your answer. That's always a great idea. So we're going to find A times E. Each column of A times E should be A times the corresponding column of E. That's just the definition of matrix by matrix multiplication. And in columns 1 and 3, there's nothing really interesting happening because you're just multiplying columns of A by columns of the identity matrix, which doesn't change these results. But the interesting thing happens in column 2, where you're getting like this 1 here means we're getting the original column 1 of A, but then we're subtracting E over F times this third column of A right here. And that gives you this minus E over F times F, which just cancels out to be 0. So this was an example of a matrix multiplication doing like a column reduction operation, sort of like turning this into something that's a little bit more like the identity matrix. And does that agree with Theorem 2.16? Sure does. Because the column operation that is done to the identity to get this is replacing column 2 with negative E over F times column 3 plus column 2. And that is the same thing as if you do A and do that column operation, you'll get A, E. And that's what Theorem 2.16 says. Okay, let's get the determinants of all of these things. For the determinant of A is a triangular matrix because it has all zeros on one side, so all the non-zero stuff is in the lower triangle, so it's a lower triangular matrix, and the determinant is the product of the diagonal entries A, D, and F. Adv. Then the determinant of E is, well, it's also lower triangular, and the product of the entries on the main diagonal is 1. You could also say that it's the result of doing a column replacement operation, column multiplicity operation, which does not change the determinant from the determinant of the identity matrix, which is, of course, 1. And what is the determinant of AE? Well, it's still lower triangular, so the product of those diagonal entries is still A times D times F. And what I notice here is that the determinant of A times E here is equal to the determinant of E, also known as the number 1, times the determinant of A. You could also write it the other way if you want to keep A and E in alphabetical order. And yeah, that's what I notice. So it turns out this works out in general, not just with this example and the exercise 2 warm-up, but it works for any elementary matrix of the same size. And we'll prove that in the next video.